How is min of two integers just as fast as bit hacking? I was watching a lecture series on bit hacking, and came across the following optimization for finding the minimum of two integers, which said to be faster than. Since the min function can handle more than just two integers, floats, strings, lists, and even custom objects, I assumed that calling min x, y would take longer than the optimized bit hack above. To my surprise, they were nearly identical. This is true even for numbers greater than 255, pre-allocated Python integer objects. How is it that a function so versatile like min can still be so fast and optimized? Note, I ran the above code using Python 3.5. I'm assuming that this is the same for Python 2.7+, but haven't tested. I've created the following C module. Compiled it, and installed it onto my system, an Ubuntu VM machine. I then ran the following. While I understand that this is a VM machine, shouldn't there still be a greater gap in execution time with the bit hacking being offloaded into native C?
Let's do a slightly deeper dive here to find out the real reason behind this weirdness, if any. Let's create 3 methods and look at their Python bytecode and runtimes. The output from this program is Here are the running times of each of these functions. Func2 is the fastest because it has the least amount of work to do in the Python interpreter. How? Looking at the bytecode for Func2, we see that in either case of x greater than y, or x less than y, the Python interpreter will execute 6 instructions. Func3 will execute 11 instructions, and is thus almost twice as slow as Func2. In fact, it's extremely close to 137.0 times 11, 6 equals 251 ns. Func1 has just 5 Python instructions, and by the logic in the previous 2 points, we might think that Func1 should probably be the fastest. However, there is a call underscore function in there. And function calls have a lot of overhead in Python, because it creates a new eval frame for the function call. That's the thing that we see in the Python stack trace, a stack of eval frames. More details: because Python is interpreted, each Python bytecode instruction takes a lot longer than a single C/asm statement. In fact, You can take a look at the Python interpreter source code to see that each instruction has an overhead of 30 or so C statements. This is from a very rough look at cval.c Python main interpreter loop. The for loop executes one Python instruction per loop cycle, ignoring optimizations. This URL. So, with so much overhead for each instruction, there is no point in comparing two tiny C code snippets in Python. One will take 34 and the other will take 32 CPU cycles, because the Python interpreter adds 30 cycles overhead for each instruction. In opc module, if we loop inside the C function to do the comparison a million times, that loop will not have the Python interpreter's overhead for each instruction. It will probably run 30 to 40 times faster. Tips for Python optimization. Profile your code to find hotspots, refactor hot code into its own function, write test for hotspot before that to make sure refactor does not break stuff, avoid function calls from the hot code, inline functions if possible, use the dis module on new function to find ways to reduce the number of Python instructions, if x is faster than, if x is true, surprised? And lastly, modify your algorithm. Finally, if Python speedup is not enough, re-implement your new function in C. PS, the explanation above is simplified to keep the answer within reasonable size. For example, not all Python instructions take the same amount of time, and there are optimizations, so not every instruction has the same overhead. And lot more things. Please ignore such omissions for the sake of brevity.
This is likely due to how the min function is implemented in Python. Many Python built-ins are actually implemented in low-level languages such as C or assembly and use the Python APIS in order to be callable in Python. Your bit fiddling technique is likely very fast in C, but in Python the interpretation overhead of the statement will far exceed the overhead of calling even a complex function implemented in a low-level language. If you really want a fair test, compare a C program, or C Python extension implementing that technique to your Python call of min and see how it compares. I expect that will explain the result that you see. Edit. Thanks to @2BitAlchemist, I can now give some more details on two additional reasons this bit twiddling will not work well in Python. It appears that integers are not stored in the obvious way but are actually a fairly complex expanding object designed to store potentially very large numbers. Some details on this are findable here, thanks to 2BitAlchemist, though it appears this has changed somewhat in newer Python versions. Still, the point remains that we are most certainly not manipulating a simple set of bits when we touch an integer in Python, but a complex object where the bit manipulations are in fact virtual method calls with enormous overhead, compared to what they do.
Well, the bit hacking trick might have been faster in the 90s, but it is slower on current machines by a factor of 2. Compare for yourself. On an average 0.277 seconds in the naive implementation, but 0.442 seconds for the optimized implementation. Always have a grain of doubt in CS classes. At least since the CMOVs instruction, added with Pentium Pro in 1995, there is no chance that the bit hacking solution could have been faster. On an i5-750, GCC, Debian 5.2.1-23, 5.2.1 20,151,028. afterthought, compiler developers are very smart people, who spend their working days finding and implementing optimizations. If the bit hacking trick were faster, then your compiler would implement min this way. And you can safely assume that the compiler understands what you are doing inside the loop. But the people working for Intel, AMD and so on are smart, too, so they will optimize important operations such as min and max if they see that the compiler hackers do weird hacks because the obvious solution is slow. For the extra curious, this is the generated code for the optimized implementation with O3. And the naive implementation with OS, O3 is huge and full of SSE instructions I would have to look up.
Here are some timings on Python 2.7, cause I assumed wrong, I'm sorry. What does this mean? It means almost all of the cost is in calling the function. The physical fastest Python can go here is 0.066 USEC per loop, which add achieves. Your min function in C is going to have less overhead because it doesn't deal with arbitrary arguments in CMP, but more overhead because it generates a new integer, rather than just returning the old one. PyArg_parse tuple probably isn't fast, either. The actual C instructions for comparison or bit shifting cost effectively nothing. They're free. Amdahl's law is laughing at you. Meanwhile, PyPy takes roughly 0.0003 USEC per call to min, or 200x less time. Evidently the C instructions are at least that cheap, since they compiled to good machine code. Maybe I'll put it another way. What's more expensive than a branch or comparison? Allocating, which Python does to allocate the function's frame and to allocate the tuple to store the arguments in. String parsing, which PyArg_parse tuple does. varargs, also used by PyArg_parse tuple. Table lookups, which PyLong_ from long performs. Computed gotos, performed by Python's internal bytecode dispatch, and I believe 2.7 uses a switch statement, which is even slower. The body of min, implemented in C, is not the problem.
If you want to say more,